we're going to refactor the program.cpp file in this lesson. So open up the lesson 1.2 project and open up the program.cpp file, and you'll immediately notice that this looks a bit different than the last version. This is a bit more extensible going forward, and this is the program.cpp file that you'll see used throughout almost all of the rest of the demo applications. We're still including the comma.h file, but we're including the rendering game.h and gameException.h files as well. These two files come from the library project. It's the first time we've really seen additional classes coming in from the library project. In the library project, all of those classes reside in the library namespace, which is why we have a using namespace library here, because the gameException class specifically resides inside of the library namespace. The gameException class is just caught here for doing a simple message box whenever there's a problem. And the rendering namespace contains the rendering game class, which is being pulled in with the rendering game.h file. So let's explore what these things are. Before we explore what these are, let's look at the CRT-DBG includes that are going on here. CRT-DBG is a memory leak detecting library that's very easy to use and very helpful. All you need to do is include this block of code and then include this block of code in order to enable CRT-DBG. What happens if there's a leak then is when the application exits, you'll see in your output window if any memory had been leaked. Gone is all of the code that we had applied directly from GL3W and GLFW. Instead, we have an std unique PTR game variable that's encapsulating an instance of our rendering game class. So if you're unfamiliar with the std unique pointer, this is coming from the memory include. And what this is a smart pointer that has exactly one instance of the game instance at any given time. So what happens now is whenever this variable goes out of scope, then its destructor is called, the corresponding rendering game class's destructor is called. And this works even if there are exceptions that are happening inside the current stack frame, so very good to use when you can. The std unique pointer is part of the STL, part of the standard template library, and it's specifically a smart pointer. And that smart pointer, whenever it goes out of scope, then it invokes the corresponding object's destructor. This works even if there are exceptions in the current stack frame, so very good to use. Now notice then there's only really one call inside of this refactor program.cpp, and that's game run. And game run, if we go step through this code here, game run comes from the game.cpp file. In the game.cpp file, it's all inside of the library project. So if we go to the library project under MISC, you'll see game.cpp and game.h. All right, so game.cpp and game.h. And those are these files that I have up on the screen right now. The declaration of game.cpp looks pretty complicated, I know. We'll go through most of this interface as we progress through the lessons. But right now, I just want to look at the run method. So the run method inside of game looks a bit like this. And this should look pretty familiar now. So we've got a while loop that looks awfully familiar from the previous one, where we're looking for the command that the window should close from the GLFW framework. And then we're also calling GLFW pull events. So very similar, but there's a few things that are happening in between here. And there's some things that are happening beforehand. Specifically, we're calling initialize window now. An initialize window is a protected method that is virtual, so it can be overridden by any derived class. And if we look at initialize window has the GLFW init call. Instead of GLFW init doing a halt or returning a -1, we're throwing a game exception. And that game exceptions message has a nice little helper string that says the GLFW init call failed. The next call here is a little different for GLFW create window. Recall from the previous lesson, GLFW create window, we specified a screen width and screen height. Well, now these are class members to the game class. Next is, instead of a hard-coded string that specifies the window title, we're going to specify the mWindowTitle class member. And finally, if you recall, this fourth variable, this fourth argument was null previously, and now it's dependent on the isFullScreen member. So if it's full screen, we call the GLFW getPrimaryMonitor function. Otherwise, it's null again, right? So if it is full screen, then the GLFW getPrimaryMonitor specifies that we'll use the primary monitor in full screen mode. The primary monitor being, if you had a multiple monitor setup, 2 or 3 monitors, it would be whatever you specified as your primary monitor. Now, if that fails, then we're going to invoke shutdown and throw another game exception. You'll see why we're calling shutdown here in a moment, and I'll explain that. The next thing that we do is call center window. Center window is part of the game class as well. And the center window command does exactly what it sounds like. It puts the window inside of the middle of the screen. We call GLFW to set that window's position from the output of the center window call. So most of these calls look familiar, just refactored a bit and stuck inside of this game class. All right, so the next call that we want to explore is the initialize OpenGL function. And the initialize OpenGL function, its first call is glfw make context current. So just as before, we're going to call glfw make context current and then call gl3w init. But if gl3w init happens to fail, then we'll throw an exception instead of just halting or returning a negative one. Get integer v, what this call is going to do is actually query the driver for the major and minor versions of OpenGL. So my video card here should be returning OpenGL 4.4 for the major and minor versions. We're going to store those in case we wanted to query them from the game class later. I'm not going to talk too much about the depth buffer. I'm going to come back to that here in a little bit, but note that the GL viewport is just like the previous call, except for this time around, instead of hard coding the size of the screen, we're using variables for mscreen width and mscreen height. And the next call is something new. This is glfw set key callback. So set key callback is, if you're familiar with function pointers, then this will make a lot of sense to you. This is a callback. Specifically, our callback is the game : on key function, which is this guy right here. And glfw, whenever it pulls the events that are related to the keyboard, it's going to then call the callback that we've specified. Now, the callback that we've specified here actually does something a little bit special. If you're unfamiliar with this syntax, this is C++11 syntax that actually does something like a C# or a Java for each loop. In C++, this is done in the STL using iterators, and you may be familiar with the STL's iterators for vectors and std maps, where we have a begin call and an end call against a container. Now, mKeyboard handlers in this example is a container. If we go look at that, you can see what type it is. It's an std map, and it has a pointer to a keyboard handler and then a keyboard handler. So this is its key, and this is its value. And this keyboard handler is just a type def to an std function. This might look a little bit strange as well if you're unfamiliar with the functional include. That's where std function comes from. An std function is nothing more than a wrapper to a function pointer. And in this particular function pointer, it returns void and takes 4 integer arguments. So our keyboard handler is modified, our set of keyboard handlers is modified through the add keyboard handler and remove keyboard handler calls. What we're going to do here is keep track of a list of handlers that are registered with the game class. Whenever the onKey callback is invoked by glfw, we iterate through that entire list of keyboard handlers and then simply pass through the invocation to every one of those handlers. In this way, we can have multiple components, multiple classes, all registering keyboard handlers to the game class and all get invoked on the very same key press. So this is the end of initialize OpenGL. So the next thing that we want to do is look at the initialize method. So this is a third initialization method. What the initialize method does is it iterates through a series of game components. And a game component is a mechanism that we're going to use to extend our applications in a modular fashion. With game components, we can encapsulate functionality for updating and drawing elements inside of a different class. We don't have to have all of that component inside of one large program.cpp, for example. So what our mComponents list is just an std vector. It's an STL vector for, let me pull it up here. It's just an STL vector of game component objects. And our game component looks like this. Our game component has an enabled flag, and it has a pointer back to the referencing game, and it has these 2 virtual methods for initializing and updating the component. Now, these aren't pure virtual. They're expected to be overridden, but they're not pure virtual in case they don't have any particular initialization or update. The idea of the initialize method is maybe that game component needs to initialize some internal state before it can be used. The update method means that instead of drawing, there's a difference between drawing and updating here. Drawing refers to rendering any components, rendering the game component, while update refers to maybe keyboard handling or collision detection. Anything that is not rendering related would be done inside of the component's update method. So what we do inside of our game class initialize method is simply invoke that underlying component's initialize. Back to the run method. Inside of the draw loop, we're going to look at these mGameClock update game time. The update game time is part of the GameClock class, and notice that the GameClock class has a reset method. Those are pretty self-explanatory that we're updating the game time. We're resetting the game clock before we enter the game loop. The mGameTime class, though, let's spend a little bit of time talking about what that is. The GameTime class looks like this. It has 2 important members here, the total game time and the elapsed game time. The total game time is the total amount of time since the clock was reset. The elapsed game time is the time between frames. So with each iteration of the frame, we have an updated elapsed time. If you were running at, say, 30 frames per second, for example, then this elapsed time would be somewhere around 32 milliseconds. All right, so back to our run loop here. Notice that after we've updated the game time, we're going to pass that total time and that elapsed time into these update and draw methods. And all of the update and draw methods do is something very similar to the initialize method, which is just iterate through a series of components. And if that component's enabled flag is set, then call update. And similarly, draw iterates through the same game components, but this is something new again. Instead of it simply treating this as another type of class, which is called a drawable game component. A drawable game component extends the game component class, and it adds to it a flag for visibility, so if this thing is visible or not. It also has the concept of a camera, which we'll get into cameras here before too awful long. But it adds this draw method, and that's what I was talking about just a moment ago when I said draw and update, we separate out their functionality. So anything that can render something to the screen, its implementation for game components is to be done inside of drawable game components, and specifically inside of the draw method. Now notice though that I'm using this interesting syntax here, drawable game component star, drawable game component, assignment equal, component as, and then this is a templated function that specifies the drawable game component type. Now what this is doing is an RTTI call. This is runtime type identification. Using runtime type information that is stored along with the drawable game component class. Now this is not standard C++ RTTI. There is a global setting that you can specify, and if I come down to the library project and I look at its properties, there's under C++ language, you'll have an enable runtime type information that can be yes or no. We're going to specify that as no. So the no for custom runtime type information means that I'm going to use my own custom runtime type information or no runtime type information at all. Well, all runtime type information allows us to do really is identify what the thing actually is. From a base class, I can ask it questions. I can ask it questions like, do you support this interface? Are you really a drawable game component? Or are you just an underlying game component? Because we know that its interface has to be a game component in order for us to iterate in this fashion. But perhaps it's a specialization, a derived class from the game component class. And the as method, and there's also an is method for RTTI, and I can look at the RTTI class. By the way, this RTTI class, its original author was Dr. Michael Gourlay, and I've simply expanded upon it. But the is and as method is what allows us to query the interface for a particular data type. So what as will return us is null if the component in this case isn't actually a drawable game component. But if it is, then I'm going to test its visibility, and if it's visible, then we'll invoke its draw method. So in this fashion, anytime we want to extend the functionality of our game, all we need to do is add components to the components vector, and they'll automatically be updated and automatically be drawn inside of our custom game loop. And then finally, we call glfw pull events in order to run the same commands as before, and then call shutdown when we exit out of the game loop. Now, shutdown is destroy, window, and glfw terminate, just as we did before, but this allows us to be extended because, as with all of those functions that we just discussed, the shutdown method is virtual. So the shutdown method can be overridden by the derived class. So let's look at an example of a derived class then and how this will actually be used. So go back to your program.cpp file and notice that I'm not invoking a game instance. Rather, I'm creating a rendering game instance. Now, the game class, you could actually invoke it directly. It's not an abstract base class, so you could invoke it directly, but I'm not going to do that here. I'm going to create a new class called rendering game. In rendering game, look at the header file here. Rendering game then says, okay, I'm deriving from the game class, and I've got a for declaration here for the game time class so that we can use it here in our virtual override of the draw method. So notice then that this rendering game class, I want to expose this public interface for the rendering game class, and I have one method that I'm going to override, and that's the draw method. So the draw method looks exactly like the program.cpp file that we had before. If we look at lesson 1.1, and we look at the program.cpp and what was actually going on inside of here, we did a gl clear buffer fv. Well, we're doing that same gl clear buffer fv call inside of our rendering game.cpp file. Then we're invoking the base class draw method and then calling glfw swap buffers. And that's it. That is our refactored rendering game class. So this allows very easy extensibility for building new programs. So from this point forward, this is the pattern that we'll be using. There's much more to come.